In 2.1 and 2.2, we talked about the idea of a limit, and we explored what it would mean for a function to have a limit at a certain x value. So as x approaches a certain value, we would check the limit coming from the right and the limit coming from the left, and if those two matched, then we said that number is the limit of the function regardless of what the actual function value is. So we want to talk in this section about continuity. We said earlier there's some functions are very well behaved, and for a function to be well behaved, it definitely has to have this property of continuity. If I was going to explain it informally, I would say that a function is continuous at any place where you can draw the function without picking up your pencil. So notice that I was tracing along this function, I get to this spot where I have a hole. Notice that even though I might draw this picture without lifting up my pencil, I can sort of like trace around that hole and continue on after it. That's different from the function being one that I could draw without picking up my pencil. Because this really does have a hole in it. Even if that hole was filled in somewhere else, I would have to lift my pencil to do it. So this, if you're tracing along and you just have the one point to jump over, that's a very specific kind of discontinuity. We call it a removable, well, let me get a different pen. We call that a removable discontinuity or a point discontinuity, because if you could use your pencil point and just like fill in that one spot, you would turn the not continuous function into a continuous function. Here we have an example of a function that seems to approach in this direction negative infinity, in this direction positive infinity. So if you have a function that approaches positive or negative infinity as x approaches a certain x value, we call that an infinite discontinuity. An infinite discontinuity. Here, this last one, if you were trying to draw here, if you're going to finish drawing the function, you have to pick up your pencil and jump to a new spot. We call that a jump discontinuity. So 3 different kinds of discontinuities that you are going to spend lots of time working with in this section. So this is the same graph we explored when we were talking about limits in the last, or 2 sections ago. Now that we have this idea, it's just an informal idea about continuity, meaning you can draw the graph without picking up your pencil. If I think about this graph now, I would notice that if I were trying to draw it, I would have to pick up my pencil here at the place where x equals 1. I could start drawing again. I'm going to have to pick up my pencil here where x equals 2. The rest of this function I can draw without picking up my pencil. So I think x equals 1 and x equals 2 are the 2 places where this function, let's call it f, is not continuous. So could you pause the video and you're going to try to find for x equals 1 and then later for x equals 2, find the limit as x approaches each of those values from the right, from the left, and then find the limit or state that that limit does not exist. You're going to pause the video and fill those in now. All right, so now that you have those, I hope you found that there's one limit that does not exist. The limit as x approaches 1 of f of x does not exist. We recognize that too as a jump discontinuity. The other discontinuity at x equals 2 is a point discontinuity. So now that you have your answers for this one written in, you've checked your answer that you decided the limit as x goes to 1 of f of x does not exist. So you're going to give your best answer for these 3 true or false questions down at the bottom of the page. We're going to check your work for those in class. Okay, so all that exploring was to kind of come to this idea of what really, if we wanted to state formally where a function is continuous, how can we do it? We have this informal idea, if you have to pick up your pencil, it's not continuous. But how do we really state it? So I want to just use this word interior. I'm going to talk for a second about an interior point. An interior point of a function is a point that's not an endpoint. So any place in the in-between parts. But if I tell you the domain of a function is from x is 0 to x equals 10, then x equals 0 and x equals 10 are endpoints. Any other point on the domain is an interior point. Okay, so formal definition, a function is continuous at an interior point if the limit as x approaches c of f of x equals f of c. So this is me saying that a function is continuous at a certain x value if the limit exists and the limit is equal to the actual function value. So the place that you were headed was the same from both sides and actually ended up being the point that got colored in. So I point out here that me saying this part, the limit as x approaches c of f of x, implies that that limit exists. So you could expand this out and say that really it has to be the limit as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x, which equals f of c. This is more compact, but then it's your job to remember that describing that limit as x approaches c implies that the limit from the left and the right match. This part implies that f of c exists, like there is some point that got colored in. And then for the function to be continuous, the limit exists, the function has a value at that c value, and those two things are equal to each other. And at an endpoint, kind of the same idea as for when we talked about a limit. If I want to think about whether a function is continuous at an endpoint, I really only have to consider the limit from the direction where the function exists. So if I tell you the domain of some function is from 0 to 10, and I ask you to tell me if the function is continuous at x equals 0, I don't need you to think about the limit as x approaches 0 from the left, because the function f isn't even defined to the left. So at a left endpoint a, you just have to consider the limit as you approach a from the right, and that's going to have to be equal to the actual value f of a. So don't worry about that too much. It should make sense given what we talked about with definitions for one-sided limits from 2.1. So we saw at the very beginning of the video that a removable discontinuity is one where there's one single pencil point missing. Zoop. Maybe that pencil point gets filled in somewhere else, maybe it doesn't. But that's what a removable discontinuity is, because if you could just change the definition, the function definition at one single point and made sure you filled in that hole, then you could change your function into a continuous function. If you have something more serious, like a jump discontinuity or some kind of infinite discontinuity, then there's nothing you can do. There's no quick fix to the function rule that will make your function continuous. And so the opposite of removable is essential. If you cannot just fix one single point in your function definition to fill in the hole, then your function has an essential discontinuity. You have no hope of fixing it, and you'll find that we most of the time choose not to do calculus on functions that have those kind of discontinuities. More on what doing calculus is in chapters 3 and later. But for now, we just want to be able to identify, is my function continuous? If it's not continuous, does it have a removable discontinuity that I can sort of fill in the blank?